Hello everyone. Last class we had seen up to problem number 9. Okay. Let's see problem number 10. That is fill in the blank. The problem is very simple, but the theory required to explain this will take some time, but it is useful to explain something else later. In order to reduce the harmonic distortion in an amplifier, its dynamic range has to be, first of all we should understand what is harmonic distortion and what is dynamic range. Okay. Just before answering this, I need to explain some theory, right? Then we will see it. Then I think this is the time to explain the meaning of what is small signal AC analysis. When I say BJT AC analysis, but indirectly I told BJT small signal AC equivalent circuit, BJT small signal AC analysis, right? What is the meaning of small signal? You will understand. Okay. Then I'll explain what is harmonic distortion. Then I'll explain what is dynamic range as well. Okay. Now don't write anything. I think this is the, what is the problem? Problem number 10. Just some theory. What is harmonic distortion and all. Okay. Don't write anything. Just listen. Let us consider a linear amplifier. Let us consider linear amplifier. If you consider linear amplifier, what is linear amplifier? Let me explain with respect to what? With respect to your output voltage and then input voltage. By default, when I say amplifier, let us say voltage amplifier. This is linear. If this is linear, then mathematically can I say V0 is equal to A into Vi, where A is nothing but voltage gain. I am not writing AB, but I am just writing for the simplicity. I am writing it as V0 is equal to A into Vi. Then, if you take, this is your input voltage Vi and this is what your output voltage V0. Then, what is the relation? Y is equal to mx. It is a straight line having a slope A, right? Now, we know that if your output voltage can switch or can swing between maximum value to minimum value, let us say power supply to ground, highest power supply to lowest power supply, let us say this is what is the range what we have, maybe dynamic range is associated to that. Means what is the maximum or what is the voltage, output voltage range such that you will not see any distortion. That is what is called dynamic range. It can be with respect to output voltage, it can be with respect to input voltage, anything. The relationship between input voltage range to output voltage range is nothing but your gain only, which is nothing but your linear gain factor, which is A here, right? We will see that point. Let us say we should bias your transistor with respect to input voltage and output voltage. Let us say this is what your mid. Then the maximum input voltage what you can cover. Let us say this is what is the maximum input voltage and this is what your minimum input voltage. Therefore, if you take this, this is what is your minimum input voltage and this is the center point and this is the maximum input. And the corresponding minimum output voltage, then the bias voltage and the maximum output voltage what you can get. Okay, this is what is the point. Now, tell me if your input is having a signal, let us say this is what is our input signal which has more dynamic range. Okay, for your understanding purpose, let me take A is equal to, example, A is equal to, let us say A is equal to 100. Example, when A is equal to 100. Now tell me, let me take and then power supply, whatever you have, power supply. Let us say this is what the highest power supply is 10 volts, lowest power supply is 0 volt. I am trying to utilize my output voltage full rail to rail, full highest power supply to lowest power supply, that is nothing but 10 to 0. Then I am giving my input voltage, therefore my gain is 100, therefore let us say this is what is 100 millivolt peak to peak. When I give 100 millivolt peak to peak signal at the input, then tell me what your corresponding output when input is swinging like this into A, that is what your output. Then your output is also following your input. But what is now? Now this is nothing but 100 into 100, 10,000 milli, which is 10 volt peak to peak. Therefore, if you speak, what is the dynamic range here? The dynamic range is what? Is 10 volt peak to peak here. This is what is our dynamic range, which is 10 volt peak to peak at the output. Similarly, what is dynamic range of at the input? 100 millivolt peak to peak, right? And remember, there is no distortion. There is no distortion, harmonic distortion. This is nothing but amplitude distortion. There is no amplitude distortion. Why there is no amplitude distortion? Let us say, for your understanding, VI is nothing but sin omega t. Then what is your V naught? A into sin omega t. If your input is having one frequency component, your output is also having the same frequency component. We don't have any harmonic component, right? Therefore, there is no amplitude distortion. There is no harmonic distortion because it is linear. And we have more dynamic range. Fine. Now, let us consider non-linear amplifier. If you consider non-linear amplifier, then what does it mean? This is non-linear. This is your output voltage V0, input voltage Vi, right? If I say non-linear, let us take, it's not simply V0 is equal to A into Vi. V0 is equal to A into Vi plus some B into Vi square plus C into Vi cube plus D into Vi to the power of 4. Let me stop with second order. This is nothing but your parabolic equation. Y is equal to AX plus BX square. I'll correlate why we get non-linearity between output voltage to input voltage from practical circuits. Or is it linear? If it is linear, very happy. No harmonic distortion, very good dynamic range, where we can have more swing at the output, fantastic. But practically all amplifiers, all BJT amplifiers, all MOSFET amplifiers, all JFET amplifiers are non-linear. Why they are non-linear? I'll explain. Let us say non-linear amplifier. Then tell me, it is a parabola, right? Yeah, if it is a parabola, let us say this is what your Vi and this is what your output voltage. Then how it is? Let us say B is negative or positive, we don't know. Therefore, let me take this kind of parabola. This is what is the parabola. Remember, this is not linear. Now this is non-linear. Then let us say this is what is my maximum input and this is what is my minimum input and the center point of your input. Let us say this is what is my center point, the bias point, the corresponding minimum output, the bias output and the maximum output what you can get corresponding to maximum input. If this is what is the scenario, then if I try to give exactly the same 100 millivolt peak to peak, if I give say 100 millivolt peak to peak, 100 millivolt peak to peak, what are you expecting? I'm expecting maximum, right? It's not 10, it will not go, but what it may be, if you see here, you'll be getting it. Let us say the output peak to peak is close to 10 volt. Actually, this will be 10, but let us say this is what is close to 10 volt peak to peak, but less than 10 volt. Close, but less than 10 volt peak to peak. Because this factor is negative, therefore it will be less than that. What out may be with respect to this point. Now, if you see here, here when you give 100 millivolt peak to peak sine wave, we are getting some swing which is close to 10 volt peak to peak or less than 10 volt peak to peak. We have gain. I'm not saying that gain is not there, but the problem is this is not a sine wave. This is distorted wave. This is what is called amplitude distortion. Don't say that the average value shifted. No. The sine wave with positive swing and the negative swing both are different. That is what is called a sine wave. No. When I say sine wave or cos wave, both the swings are equal. If both the swings are not equal, means that is having distortion. This is what is called amplitude distortion or harmonic distortion. Why it is called harmonic distortion? Mathematically I can explain. Let us say Vi is equal to sin omega t. Then means input is having one frequency component, but your output is having a sin omega t, the same frequency component of your input, plus sin square omega t. What is sin square theta or cos square theta? 1 plus cos 2 theta or sin 2 theta. Therefore, your output is not only having fundamental frequency component of your input, whatever you are giving, which is single frequency component at the input, but we are getting second harmonic fundamental frequency component plus the second harmonic also we are seeing at the output. If you take third order, third harmonic, fourth order, fourth harmonic. If you take infinity order, infinite frequency components are all harmonics you will be getting at the output. That is what is called harmonic distortion. This is what is basically amplitude distortion. This is amplitude distortion or harmonic distortion. Then if with this, let us say this is what your audio amplifier, with this if you get this, then your quality of your output sound signal will be altered. That is wrong, that is not as expected. Therefore we don't want any amplitude distortion or harmonic distortion. Then what to do? Then the simple solution what people told or whatever we are having or whatever we are dealing with, right, is nothing but apply small signal. Small signal is nothing but what? Don't apply your input this much to cover this much voltage, because we don't have dynamic range. Because you want to use this much, if you want to use this much, we need to apply this much voltage at the input. Therefore, if you want to get this much dynamic range for your AC signals, then there is a distortion. Here, yes, you can utilize this much dynamic range without any distortion because it is linear. Then, if I apply very small signal, let us say I am going to take only this portion where it is almost linear. If I take only this portion which is almost linear here, not only here, you take here or you take here, you take any smaller portion, that is nothing but what? Linear about a point, that is what is your operating point. About operating point with a small range, that is nothing but your dynamic range. Therefore you can say here when you apply a signal, small signal, you will be getting the signal without any harmonic distortion. Means if you apply small input signal, you will get amplified version of that, but still it is having a dynamic range something, but not completely rail to rail. If you try to utilize complete rail to rail, you will get harmonic distortion. To do not get any, or to do not see any harmonic distortion, your dynamic range should be lesser. Or I can say to do not see any harmonic distortion, your dynamic range is lesser. We need to apply small signal. This is what is called small signal. That's why for all your amplifiers, right, the first stage amplifier are all small signal amplifiers. We will give small signals, not large signals. If you take your BJT circuit, right, that is non-linear. Why? Because that is a PN junction diode. What is the voltage to current relationship? That is I is equal to I naught into e to the power v by eta vt minus 1, right? If you consider common emitter amplifier, I am explaining how it is non-linear amplifier. But whatever H parameter model, whatever I explained the theory, like linear amplifier, but strictly speaking it is non-linear amplifier. Indirectly it is imposed to have linearity by applying small signal input, right? That's what we will see. This is what is your RC, VCC, and this is what your IC, and this is what your output voltage, let us say VC or V0, and this is what your input voltage, which is another VBE, and this is what your IB, right? This is nothing but your VBE. What is the relationship between IC to IB? IC is equal to HFE into IB. What is the relationship between V0 to IC? It is almost linear only. Your V0 AC analysis, this is what is connected to the ground, minus IC into RC here. Therefore now tell me, I want ultimately the relationship between V0 to VBE. What is your VBE? This is nothing but your input voltage, right? Therefore let me call this as your VI or VBE, anything is fine. Therefore your output voltage to output current to input current to input voltage. Therefore output voltage to input voltage. I want that to be linear. Now tell me, your output voltage is derived from output current. Why? How much current you are getting in the collector, that much drop if you take it out, remaining voltage is coming here. Therefore the relationship between IC to V0 is linear only. That is fine because RC is constant. What is the relationship between IC to IB? IC to IB is also, if HFE is constant, IC to IB is also linear. Therefore, IB to V0 is linear. What is the relationship between IB to VBE? If you take H parameter model and we told HIE, therefore VBE is equal to IB into HIE. HIE is constant, then that is also linear. But remember, this is nothing but what? PN junction diode. This is NPN. This is a PN junction diode. The voltage across a PN junction diode is VBE. Current through PN junction diode is IB. What is the relationship between? I is equal to I naught into e to the power of V by eta Vt minus 1. The relationship between current to voltage is completely non-linear. How do you know? E to the power of x. What is e to the power of x? 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. which is non-linear completely. Therefore, the relationship between input current to input voltage is non-linear. Therefore, your output voltage to input voltage non-linear. Therefore, all BJT amplifiers, if you take MOSFET, ID is equal to mu n CH W by 12 into VGS minus VT whole square. That is also non-linear. Input voltage to output current non-linear. Output current to output voltage linear. Output voltage to input voltage non-linear. But I can say one thing. If x is very small, then x square x cube can be neglected. Then you will get e to the power of x as a linear component. Then you will get the relationship between VBE to IB is also linear. Therefore, indirectly we are achieving linearity from non-linear amplifier by applying small signal. If VI is small, VI square is too small, then you can neglect VVI square, then you will get V0 is equal to A into VI. That is true when you apply small signal. From the graph also I can explain. This is completely, if you want to have this much dynamic range, then you see non-linearity. Then if you have this much dynamic range, you see linearity. If this is what your dynamic range, this is linear. Therefore, for lesser dynamic range, you are getting linearity. Right? Now tell me with this, what is the answer? Now if I go back to the problem. In order to reduce the harmonic distortion in an amplifier, you'll be confused. In order to reduce the harmonic distortion, okay, fine. In order to reduce the harmonic distortion in an amplifier, its dynamic range has to be what? Option A, compressed. Option B, expanded. Option C, constant. Option B, none of the above. What is he saying? See, again, normally you will be confused. For a nonlinear amplifier, to do not see any harmonic distortion, the dynamic range should be lesser. Remember, this is not called dynamic range. Then we are applying small signal. The dynamic range is nothing but indirectly the curve which is what is like this, it should be somewhat linear. Then we can have more and more dynamic range. Right? Therefore, tell me, if you want to reduce harmonic distortion, for the same type of signal, then what I do, I will not take this much. I will take this much. Then it is having harmonic distortion. To avoid harmonic distortion, you try to increase the dynamic range. Dynamic range is nothing but indirectly we need to improve the linearity. If you improve the linearity, then your dynamic range will increase. If dynamic range is increasing for the same set of signals, then your harmonic distortion will be suppressed, reduced. Therefore, what is the answer? Its dynamic range has to be expanded. Design change. We need to change the design such that the linearity of the circuit will increase. What is the answer? Problem number 10, the answer is B. It should be expanded, right? Dynamic range to be expanded, or it should be large. Okay? Maybe if you want, I can explain a different way, but before that, you try to draw this. Okay? You take this. This is what is very important point. That's why the name called small signal analysis, to have linearity. This is with respect to signals. But now the problem is related for a given signal to do not see any harmonic distortion. If the dynamic range is more, like if that is the circuit for the given signal, if that is the circuit, then harmonic distortion is reduced. Okay, that's why understanding the problem is very important. Is speaking with respect to design side. What to be done for the design such that your harmonic distortion will be reduced for the same set of signals which are applied. I can explain in a different way, right, to understand. Now let us say this is what is circuit 1, where the relationship between Vi to V0. It is non-linear, but it is something like this. Okay. There, if you say for the same set of signals, right? For the same set of signals, right? Let us say for the same set, this is completely non-linear, right? Maybe I can say this is what is the dynamic range. This is what is the dynamic range, whatever you are having, right? This is what is our dynamic range, where it is almost linear in this portion. This is almost linear here, wherever you take. Okay. Now circuit 2, let us say your dynamic range here, example, the dynamic range is only 1 volt. Okay. Now if you take circuit 2, this is your Vi and this is your V0. It is also non-linear. I am not saying that it is not linear, not non-linear. It is also non-linear, but it is somewhat better. This is what is completely having non-linear curve, but this is not having completely non-linear. This is kind of little bit linear. Then if I say this is what is now my range is more. Range is more in the sense it is almost linear here. Therefore, this is what is my dynamic range, and this is what is your operating point. However, you are having operating point, then but the range is more here. Okay, and this is what is your operating point. Similarly, this is what is your operating point. Now if you ask me what is the range, now the dynamic range, you can say it is almost 2 volt. Therefore this is what is our dynamic range with respect to output. Dynamic range means your input can have that, your input dynamically can change, which is nothing but AC signal in this portion without any harmonic distortion. Now it can see this much. Therefore this is what is the dynamic range. Therefore now tell me for the same set of signals, let us say I am giving the same set of signals, it will see more distortion. But if you increase the dynamic range, then for the same set of signal, here the harmonic distortion will be lesser. The circuit which is having more dynamic range in the sense, in what portion, for what voltage range, your system will have linearity. That is what is called dynamic range. The system which is having more dynamic range, then remember your harmonic distortion will be lesser. That is expected because the slopes are somewhat better. It is close to linear, but this is completely non-linear. Okay. Therefore, what is the answer? Answer is B. It to be expanded. Answer is B. Now after this, write down problem number 11. Write down problem number 11. Problem number 11. A common emitter transistor amplifier has a collector current of 1 milliampere, collector current of 1 milliampere, its base current is 25 microampere, at room temperature. Then its input resistance Ri, input impedance. Okay, that is what they are asking. Okay, now see, if you take common emitter amplifier, right, this is your output voltage, this is your input voltage, okay, and this is your RC and then VCC. This is your common emitter amplifier. And the impedance in input impedance, right, Ri. If you go for simplified model, what is your input impedance? Actually, your Ri is equal to HIE plus AI into HRE into RL. This is what your input impedance, right? If you take simplified model, this is nothing but your HIE. Simplified model. Nothing is given, therefore you can take simplified model. Right? Therefore, what is your Ri? The input impedance is HIE. If you know HIE, problem is over. Therefore, to find HIE, we know that what is GM? GM is equal to HFE divided by HIE. Right? Then what is HIE? Therefore, HIE is equal to HFE divided by GM. What is HFE? HFE, we know that HFE is nothing but your beta value. Beta is nothing but you can neglect reverse saturation current, then you can take both of them same. IC divided by IB. Therefore, what is your IC? 1 milliampere. And what is your IB? 25 micro. Which is nothing but what? Micro, if you take mega into milli, it will be kilo. Then 1000 by 25. Therefore, it is nothing but 40. Your beta is 40. Similarly, we know that what is GM? GM is equal to IC by VT. What is IC? It is already given 1 milliampere. Then you take VT. What is VT? 26. But let me take approximately 25 milli. Therefore, 1 implies what is our HIE? HIE is equal to HFE already calculated, which is 40 divided by, and 1 milli by 1 by, it is 1 by 25. Then if you take this 40 into 25, what is 40 into 25? 1000. 1000 is nothing but 1 kilo ohm. Therefore, what is your input impedance? 1 kilo ohm. Your RI, right, is nothing but 1 kilo ohm. What is the answer? Answer is A. Done? Write down problem number 12. A BJT is said to be operating in the saturation region if, actually it is straightforward. How many regions we have? Actually we have 4 junctions. If you take a BJT, collector, base, emitter, this is your NPN transistor, this is a PN junction diode, this is another PN junction diode. This is your emitter junction, collector junction, right? Emitter, collector. If both are in forward bias, this is what is saturation. If both are in reverse bias, this is what is cutoff. And this is in forward bias and this is in reverse bias. This is what is active region, normal active region. And this is reverse bias and forward bias. This is what is inverse or reverse active region. That is what. Okay. Therefore, I want saturation. Therefore, what is the answer? Both should be forward bias and forward bias. Answer is D. Now, 13th problem. Okay. Now, in a BJT amplifier shown in figure, transistor is biased in forward active region, means active region, comma, putting a capacitor across RE will, what he is saying is, if you have this is what your circuit. I'm just simplifying it. VCC, this is what is our RC and then RE, and this is what is our V0. Okay, anything is fine. Okay, this is what is our V0, and this is your V in. This is your R bias. Okay, then what is speaking about voltage gain and input impedance. For this, if you don't keep any capacitor, tell me what is your voltage gain. This is nothing but what? This is nothing but CE with RE amplifier. This is nothing but your feedback resistor. That will decrease the gain, no doubt. And we know, right, that is nothing but AV is equal to minus RC divided by RE. And what is your input impedance? Your input impedance we already calculated, right? The impedance seen into your transistor. That is nothing but what? You remember HIE plus 1 plus HFE into RE. This is what is the input impedance of C with RE amplifier. The moment when you keep capacitor in parallel, let us say a capacitor is kept in parallel, then it is what is bypassing it, right? Then that is what is bypassing it. This is simply in AC analysis, this is nothing but C amplifier. Now there is no feedback in AC analysis, only feedback is present for DC analysis or operating point. But now the problem is related to AC analysis. Then tell me what is the voltage gain for common emitter amplifier. Your voltage gain is nothing but what? Minus HFE into RC divided by HIE. I am taking simplified model. Then what is our input impedance? If you take input impedance, that is nothing but simply HIE from simplified model. From all are simplified model. Therefore, we are taking simplified model only. Both these two formulae are for both simplified model. Okay, simplified model. I can take simplified model. Okay. Therefore, now what is the conclusion? If you keep capacitor in parallel to RE, your voltage gain is decreasing. Your voltage gain will increase because there is no feedback. If there is no feedback, your gain will increase, but it is not stable. Remember, this is stable, but this is unstable. But your gain is more, but it is more, what it may be. Now this is high, but now your input impedance is decreasing. Therefore, the moment when you keep capacitor in parallel to RE, there is no feedback, there is no negative feedback, your voltage gain will increase. What is the answer? Yeah, B, your voltage gain is increasing, or D, and your input impedance decreases. Your input impedance decreases. Answer is B. Therefore, what is the answer? B. Answer is B. Your voltage gain increases, but your input impedance decreases. Done? Okay. Problem number 14. From measurement of rise time of output pulse of an amplifier whose input is small amplitude square wave, one can estimate the following parameter of the amplifier. Okay, gain, bandwidth, product, slew rate, upper 3 dB frequency, lower 3 dB frequency. Okay, from the rise time. Okay, let me give you something. If you consider low pass filter, then I'll go to amplifier. Okay, if you go to low pass filter, what is low pass filter? This is your resistor and then capacitor. Okay, and this is your C and R, and this is what your V0, and let us apply what you call a step signal. When apply step signal 0 to something, this is nothing but 0 volt to something, let us say some 10 volts. Then what is your output? When you apply step signal, what is your output? Your capacitor will be charging slowly, right? Your capacitor is trying to track your input. Your capacitor is charging exponentially and then trying to track your input. This is what is your 10 volt and this is 0 volt. But how much time it will take to reach 99.9% of final value? That is nothing but 5 times of time constant, where time constant tau is nothing but RC. That is fine. And if you speak, this is what is with respect to transient analysis. What is rise time? 20% to 80%. Right? That is what. And if you take the frequency response of this is nothing but your low pass filter. This is transient domain explanation where you have the rise time. This is what is your rise time, how much time you have from 20% to 80%. This is what is your rise time. Therefore transient analysis. But now if you ask me from frequency response, this is nothing but low pass filter, which is what is having the frequency response something like this. If you take Bode plot or whatever, this is what is having 3 dB frequency. This is nothing but higher cutoff frequency, which is 1 by 2 pi RC. This is nothing but your bandwidth also. What is your bandwidth? FH only. This is what is your bandwidth. This is what your low pass filter, right? And we know the relationship between rise time to higher cutoff frequency or rise time to bandwidth. What is that? This is what your transient analysis and this is what your frequency analysis. Therefore, what is that? Your rise time is equal to 0.35 divided by bandwidth, which is nothing but 0.35 divided by your higher cutoff frequency. If you know rise time, then we can calculate FH. Therefore, if you know rise time, your FH will be 0.35 divided by rise time. That is what you get it, right? Okay. Now, if you consider your common emitter amplifier, right? Now, this is what your RC, and let us say this is your V0, and this is what your VCC. And we have seen, right? We have all. If you take completely RC coupled C amplifier, we know what you call. This is what is your frequency response, right? And this is what your voltage gain. And tell me what is the reason to have this? The reason for this is due to coupling capacitors. Due to coupling capacitors, your lower cutoff frequency, this is nothing but your FL, due to coupling capacitors. But I don't bother. But it's not asking about coupling capacitors, let us say. But this is what is due to what? This is due to BJT internal caps. Due to BJT internal caps. Therefore, this is what is defining your higher cutoff frequency. BJT internal caps means, let us say it is having some cap, load cap, due to parasitic cap. And it has, this is what your amplifier, and it has output impedance also. This is nothing but your R0, the output impedance. Therefore, output impedance, resistor, the combination will give you a low pass filter. That's why your high frequency response, or you can say, see, because of low pass filter, your high frequency response is having decrement. Means as frequency is increasing, our gain is decreasing. Similarly, why gain is decreasing? Because of R0 CL combination or because of BJT internal capacitance. Therefore, it is having higher cutoff frequency. Therefore, what is the answer? From the measurement of output pulse of an amplifier, the rise time tracking means that is because of low pass filter, right? Square, one can estimate the following. What is that? Upper 3 dB frequency, your higher cutoff frequency, right? Therefore, from the rise time, you can calculate higher cutoff frequency. Therefore, what is the answer? For this amplifier, if you give, what do you call? What is saying? A pulse, something like this. If you give like this, what is your output? Your output will be trying to track to it. Therefore, the rise time at the output is defined because of the VGT internal caps are due to higher cutoff frequency. Therefore, answer is C. For the high frequencies, which is nothing but step, that is nothing but your high frequency, the transition, the rise time, your output is trying to track to it, right? Then that is nothing but rise time which is compatible to your low pass filter. Then the higher cutoff frequency is the one which is what is giving the relationship between rise time to upper 3 dB frequency. Done. Now the last problem for chapter 2, level 2. Problem number 15. A distorted sinusoid has the amplitude A1, A2, A3, etc. of the fundamental, second harmonic, third harmonic respectively. Then the total harmonic distortion is. Okay, just before that, okay, just to explain, if you take linear amplifier, this is your V0 and then Vi, right? What is V0? V0 is equal to A1 into Vi. Okay, then what is your harmonic distortion? The total harmonic distortion actually 0. There is no harmonic distortion. Therefore, no distortion. Because there is no second harmonic. What does it mean? That means if input Vi is something sin omega t or cos omega t, then what is your V0? V0 is A1 into sin omega t. That's it. Right? Therefore, what are omega naught, let us say, and then sin omega naught. Therefore, this is what is having one frequency component omega naught. This is also having same frequency component of f naught or omega naught. Anything is fine. No harmonic distortion. Case B, non-linear. This is non-linear, but only second order. That is what we had seen before. Let us say V0 is equal to A1 into V1 plus A2 into VI square. Okay. Let us take only second order. Then you know what is harmonic distortion? Your total harmonic distortion is, it should be A2 should be 0 ideally. If A2 is 0, then this is nothing but linear amplifier. But A2 is there. Because of this you are getting, right? That is what your harmonic distortion. This is what is explained like A2 divided by A1. This is what your harmonic distortion. If A2 is increasing and A2 is comparable to A1, then you have significant harmonic distortion. What does it mean? If your VI is just sine omega naught t, which is what is having simply F0, then what your V0? Your V0 is having what? A1 sine omega naught t plus, therefore A1 sine omega naught t plus A2 sine square omega naught t. If you calculate, you will get sine omega t, therefore it is going to have F0 and 2F0, second harmonic also. Therefore, we don't want this A2. Therefore, A2 divided by A1 is nothing but your harmonic distortion. Now, let us take higher order. If you take higher order, but non-linear. If you take higher order, this is nothing but your V0 and then Vi. Then V0 is equal to A1 Vi plus A2 Vi square plus A3 Vi cube, etc. Then what is your total harmonic distortion? Your total harmonic distortion is defined as A2 square plus A3 square, etc. root divided by your A1. This is what is your total harmonic distortion. What does it mean? If Vi is simply sine omega naught t, which has only F0, but your V0 will have A1 sine omega naught t plus A2 sine square omega naught t, etc. Therefore, it has F0, 2F0, 3F0.